Good morning, everyone. And first, I would like to thank the organizers for selecting my talk, and then also thanks to Girish for making my life a bit easy. He has already introduced the simulation, which I will talk about. And as you can see, I have changed the title a bit to my talk, and this is because this guy, my supervisor, uh, Eli Sovet at the Ben Gurion University Department of Physics. He wanted me to talk about the recent works in the 21 centimeter field, and uh, I mean, he wanted me to, talk about some of our works in this 21 centimeter field and line interdisciplinary field in general. Okay, and I will be basically talking about a code that we have been developing for some time. Okay, and will be mostly focusing on that, and then we'll show some of the applications that we have already published, and then some works that are ongoing using that code. Okay, and this is our group at the Ben Gurion University Department of Physics. Okay, so these are the names of the different guys that I'm working with. Okay, so as the title suggests, I'll be exploring the delaying and the heating, mechanism or effects on the 21 centimeter signal using a modified version of the 21 centimeter fast code. Okay, so this is a semi-numerical code as Girish already described. Okay, and so let us first start with what are the delaying effects that I'm going to discuss today. So the first delaying effect is the relative velocity between the dark matter and baryon. And so as you know that the baryon acoustic oscillation that occurs due to the interaction between the baryons and photon fluids before the recombination, it generates supersonic relative velocities between dark matter and baryons just after the recombination. Okay, so just after the recombination, there is a relative velocity because of this interaction. And if you sit at the center of mass of the dark matter, or the rest frame of the dark matter, you will see that the baryons actually stream away from the dark matter's center of mass or gravitational field due to this, relative velocity. And the average value of this velocity is roughly 30 kilometers per second. And it has broadly three effects on the early halos that formed, okay, early in the hierarchical structure formation scenario. So as the baryons stream away from the dark matter potential, less gas is able to settle and collapse into the halos, which decreases the gas fraction. Okay. The second effect is due to the streaming effect, the minimum halo mass that can contain cool gas is now increased. And the third effect is that this velocity creates an additional non-thermal pressure, which prevents the collapse of matter below a certain length scale. And this basically decreases the number of halos at this scale. So this is basically some, so this effect is basically delays the structure formation or the onset of the cosmic dawn epoch, as you will see. And that's why it is called a delaying effect. So second such delaying effect is the Lyman-Warner radiation. So the stars emit UV photons in the Lyman-Warner band, which is from 11.2 to 30.6 electron volt. And radiation in this band, what it does is it eventually photodissociates the molecular hydrogen and disturbs the star formation in small halos, okay, which formed earlier. And as the universe evolves, more and more Lyman photons are emitted, and this raises the minimum halo mass, and until the mass reaches the atomic cooling threshold. So this again, okay, disturbs the star formation in the small halos, and it basically delays the cosmic dawn and the subsequent epochs. We'll see this. So these are the main two delaying effects that I am going to show. And then there are like heating effects. Okay, so as you already know that there is X-ray heating, so I'm not going to talk about that. So I'm going to talk about two more heating effects that people have incorporated in the 21 centimeter calculations. One such is the Lyman alpha heating. Okay, and as this suggests, it is uh, by the Lyman alpha photons. So the ultraviolet radiation from the first stars, they resonantly scatter with the hydrogen atoms as these radiations redshift into the Lyman alpha line. And during this process, what happens is that they increase the excuse me. Yeah, sorry. And as this happens, they basically during this process they heat up the intergalactic medium. Okay, and there are broadly two types of Lyman alpha photons. One is continuum and this injected. The continuum photons tend to heat up the IgM. Injected photon mainly cools the IgM, and on average we expect more continuum photons. So this Lyman alpha heating on average it heats up the intergalactic medium. Of course, it depends on several other things like X-ray heating and but yeah, this heats up the medium, and the rate of the heating depends on the shape of the spectrum, the vicinity of the Lyman alpha line. And another heating is the CMB heating, which is basically a mechanism in which the Lyman alpha photon it transfers energy between the radio background and the thermal motions of the gas, and this in turn heat up the gas. So it basically Lyman alpha photons basically transfer an energy from the CMB to the thermal motion, and it basically heats up the gas. Okay, and in the absence of X-ray heating, this paper it claims that it has a 10% efficiency in heating the gas. However, recently, Avery Maxine made some improvement in the calculations, and he showed that this effect is not very efficient or not at all efficient. Okay, so this is the CMB heating. So this is the second heating effect that I wanted to say. All right. So now what I will talk is the 21 centimeter. So this is a baseline code using which we will make prediction for the global signal and the power spectrum. Okay. And the basic baseline 21 centimeter code, it already incorporates the delaying effect that I've already discussed, but it does not, well, the public version that it has, it does not include the heating effect that I just so that's the new thing that we can implement. And another problem with this public version of the 21 centimeter fast code is that, of course, I mean, it accepts these cosmological parameters and astrophysical parameters, and it basically predicts this global and the power spectrum. However, they use some pre-computed tables for these, say, transfer function, collapse fraction, etc. And these tables are okay provided for a single set of cosmological parameters. Okay, if you see the public version of the code, these tables are supplied for a single version of cosmological parameters, and yeah, and the code to calculate these input tables are not provided there. Okay, so that's a problem. And to solve this, what we did is basically we yeah, so basically we interface the 25 centimeter fast code with this class. Okay, so you know class is Postman solver code which gives you these beautiful CMB prediction. And class is easy to deal with. Okay, you can change class very, easily and efficiently. So we basically interface class with 21 centimeter class fast. And now what we do is that for any cosmological parameter, if you change the cosmological parameter, it calculates all the quantities on fly and just feed it into this 21 centimeter fast calculation. Okay, so now and also we have implemented this Lyman alpha and the CMB heating. And the CMB heating still, I mean, since it is debatable, so I just made it a bit not so prominent. All right, and due to this class interface, what makes it more useful is that you can now use physics. We understand lambda CDM models, and you can basically have predictions or do these calculations inside class and then feed into the 21 centimeter fast. But of course, I mean, you have to make some certain changes inside 21 centimeter fast calculations also. But now the code looks more flexible with this interface. Okay, and another thing that is important is that due to this interface, now it is possible to jointly analyze the class or the CMB and the 21 centimeter data together. Okay, starting from a same initial condition. Okay, or same parameters. And so it's basically important that we can now do the joint analysis of the same data 21 centimeter fast data. And the importance of this has already been talked in OTDEP's, I mean, OTDEP actually talked this importance of this joint analysis of CMB and 21 centimeter data. Right. So now with this code in hand, we made some, basic plots, and just to showcase how this Lyman alpha and other things, Lyman-Warner feedback and other things, act. So this is the global signal without feedback, and you see these different epochs I have pointed out here. And when you apply the Lyman-Warner feedback, what happens is that since it is a delaying effect, basically delays the onset of the cosmic dawn and it basically shifts the signal altogether. The same happens with the relative velocities. If you apply the relative velocities, again, things are shifted. So these are the kind of delaying effects that I was talking about. Now, what happens if you apply the CMB and laminar alpha heating? And this is obvious. I mean, the heating will increase the temperature, and yeah, the curve will look like this after applying the CMB and laminar alpha heating. Right. So there will be changes in the power spectrum also. So I have here pointed out three different regions in the power spectrum where the three different processes actually dominate the fluctuations. This laminar alpha coupling fluctuations, heating fluctuations, and XC fluctuations. So this is, I mean, without any feedback or VCB. Now, if you introduce VCB and feedback, you see that all these features are shifted, okay, towards the low redshift. And if you apply heating, you see there is like amplitudes are damped, which is what heating does, okay, to the power spectrum. All right. So now with this code in hand, we basically did this first project, which is exploring delaying and heating effects on the two-inverse integral signature of the fuzzy dark matter. So already, Otsuri pointed out in his talk what is the problem with the CDM picture of cosmology. And there are, of course, various possible solutions to it. One such solution is this fuzzy dark matter. So in the FTM model, the dark matter is composed of alpha light particles with mass as light as 10 to the minus 22 electron volts. And due to the small mass, this FTM has a de Broglie wavelength of order of kiloparsec, below which it behaves like wave, and above which it shows the characteristic of CDM. And due to this, what happens is that due to this wave nature, FDM suppresses the growth of structures on small scales, and it tends to solve these problems of CDM. Okay, so we actually did implement this FTM calculations into this modified version of the code. Okay, and all right, and so we basically modified this transfer function mainly. Okay, and we did all the calculations and fit into the 21 centimeter flux and made prediction for the fuzzy dark matter. Okay, and so this is one such plot I wanted to show. So if you introduce fuzzy dark matter into calculation, then you see that things get delayed because the structures are washed out and cosmic dawn is shifted. So that's why. So this is the example. And for the power spectrum, it does the same. It further shifts the signal. And yeah, and the laminar Warner feedback and the relative velocity, they do not affect the FTM models. It is obvious, but the heating affects both. So there is a difference between the CDM and the FTM model, as you can see. And you can basically calculate quantities like chi-square, which is the difference between two models and the expected noise that you have. And then this basically statistically says whether it is possible to distinguish between the CDM and FTM models for the power spectrum as well as for the global signals. And as you can see, these predictions actually global signal. So power spectrum is more is better than the global signal in distinguishing between this CDM and FTM model, and this depends also on the different cases that you consider. And we made a Fisher analysis, and we showed that if the FTM particle mass is 10 to the minus 21 eV, then Hera should be able to determine the FTM particle mass within 1.2, 5.6, and 7.9 in the optimistic, moderate, and pessimistic foreground scenarios, respectively at 1 sigma confidence. And heating, it basically worsens the constraints. And if you consider the different FDM masses, then and you make the chi-square plots like this, then then we showed that Hera will be sensitive to FDM particle masses most optimistically up to 10 to minus 19 to 10 to minus 18, depending upon, of course, different foreground assumptions and different feedback scenarios. Okay, so with this, we move on to the next project, which is measuring the cosmic expansion using the 21 centimeter velocity acoustic oscillations. So the fluctuations in the dark matter baryon relative velocity field, as I mentioned before, these fluctuations are imprinted at oscillations just like VAOs. They're called the velocity acoustic oscillations, and these are the velocity acoustic oscillations in the 21 centimeter power spectrum at large scale. And this paper first proposed that these velocity acoustic oscillations in the 21 centimeter power spectrum can be used as a standard ruler to measure the expansion rate of the high redshift. Okay, and we basically did this same. We made, so this is the global signal and the power spectrum, and the power spectrum is plotted at a redshift called Z half, and Z half is basically where the T mean is half, T21 is half the T mean value. Okay, and as you can see, these VOs are very, prominent, and at this Z half, it is, the VO features are more prominent. Okay. Uh, all right. So we made these VAOs, and what we can do is that we can model these VAOs, and then we can perform an alpha proximity test on the 21 centimeter power spectrum, and it will provide us information on the expansion rate, which is the Hubble expansion times the RD. Okay. And yeah, so we basically use the same pipeline. Now we are using a mock data and an NCMC analysis to, get the constraints, not constraints, I mean, the error with which we can measure this expansion history. And yeah, so this is kind of the main result of this analysis. So we have two cases with and without Lyman heating, and for different feedback scenarios, and for three different foreground assumptions, it is possible to pinpoint this expansion history with, very, very good accuracy. And then we changed the simulation parameters, and we made several simulations, and we denote each simulation with its minimum temperature and the Z mean, which is corresponding to the minimum temperature value. And we showed that it is possible to measure this expansion rate within this Z mean range, or rather it should be Z half range, with like 1.53% and 6% accuracy with the optimistic, moderate, and pessimistic foreground respectively. Okay. And we also estimated the uncertainties introduced in this measurement due to the uncertainty in the cosmological parameters that we have in Planck, and those uncertainties will introduce a 0.08 to 0.2% relative float, okay, in this measurement, which is significant given these good accurate values that we have. Yeah. So until now I was talking about mostly the mock data. Now I will move into the real data, the HERA data that Gish was talking about. So we basically developed a machine learning based accelerated Bayesian interface, and this interface provides us neural networks of the 21 centimeter global quantity. Okay, and we train the emulators, and we analyze the data, and we have the bounds on the different parameters. So this paper, this talks about the HERA data that Girish showed, and this paper actually made this analysis based on this HERA data, and we basically repeated their analysis with our this interface, and we got almost similar results that the HERA people got. And I'm basically working with this type of work on this, and this is like ongoing project. And the second is the joint analysis of the 21 centimeter and the CMB data. And the idea here is that you can supply information from the 21 centimeter observations to the CMB analysis, and which will improve the CMB constant. And in turn, the improved CMB constant will help to improve the 21 centimeter constants, for example, like astrophysical parameters or so. And an example, like in the same analysis, you have this degeneracy between AS and the tau reionization, right? Now the CMB observations, what it can do is that it can provide information about the reionization and the tau reionization. Okay, and if you supply this information, then you can possibly break this degeneracy, and you can also shrink the error in AS. So this is one of the advantages of this, joint analysis. Okay, 1 minute, and then you can also constrain the neutrino masses, so that can be, neutrino mass and tau reionization are degenerate, and if you supply the information on tau reionization, then neutrino mass constraints can be improved. And the last work is basically we have used, voxel intensity distribution, which is the one-point function of the observed pixel intensities of the CO line, to predict, to constrain the different, the power in the different beams of the power spectrum. Okay, and we showed that it is possible to, constrain the small scales using this simple statistics. I'm sorry, I could not talk more about this paper, but this is a really important, and interesting result, which I can discuss later on maybe. So with this, so this is the summary. So this is the main point of my talk, and this is something that we have done recently. Thank you.
So, quick questions for Debanjan. Tridip?
Yeah. So when you calculate the constraint on the fuzzy dark matter mass, did you vary all the other three parameters, or you just vary the mass only?
No, I varied the other three parameters.
Okay. And did you see any signature of correlation between any other parameters with the mass of the?
Yes, I see. Yes, I can show you the plots maybe later on.
Thanks.
Yeah, there are correlations, of course.
See, if I understand correctly, Lyman-Warner photons, they affect molecular cooling halos.
Right.
And mass of those halos are small. So how do you incorporate contribution of Lyman alpha feedback in your simulation?
Lyman-Warner feedback.
Lyman-Warner feedback.
Okay, fine. So it's basically how to. Yeah, so there are basically parametric models. Okay, so there are. I can maybe show you. Please, I have those slides. I think I have. Yeah, sorry. Yeah, so these are. So this is how I basically, incorporate the. So these are basically three parameters. So if this is the mass of the molecular cooling halo, then due to the Lyman-Warner radiation feedback, so these are the three feedback strains, and these are the parameters given, it will increase the mass. Okay. Right. So so actually the quantity of interest is, I'm not sure if I have that slide. Just let me. Okay, I think. Yeah, so these are the two things where so when we calculate the F collapse, okay, you modify the this lower bound with that parameter, okay, parametric form, and then you calculate the integration, and this affects the F collapse calculation as well as when you calculate the F star. So this is the how we define the F star, and here also this M cool appears. So these are the two places where how this is how I implemented this Lyman-Warner radiation feedback. Oh,
maybe just quickly, the Hera inference that you showed, one of the parameters, I think M-turn it was called, seemed to be constrained using Hera already. Is that significant? This middle column.
You mean this? Sorry. This?
Yeah. No. The next. Yeah, that one.
Okay, this M-turn you mean?
Yeah.
Well, so there is one thing which is the Hera data does not. I think the Hera data does not constrain this. This constraint actually comes from the luminosity function observations and then others. So we clubbed all these observations together. So Hera can actually do something here, but yeah. So all these constraints, good constraints, are coming mainly from the luminosity function observations.
Let us continue this discussion over tea and thank the speaker once again. I think we have overshoot for a few minutes. cut short
I
for a bit.
apologize for that.